Jana, that's the same one as the one in MeetEcho, right? I
It
can
should
find
be,
it.
yeah, yeah. It's the
Okay.
same one, yeah.
Yeah, I got it. Thanks.
Thanks, Jake. Thanks, Lucas. All right. It's a minute past, so let's get started. Welcome to ICCRG at IETF 112. We are meeting after about after about 8 months. So I hope you had a good 8 months, and I'm looking forward to our session today. It's a pretty packed agenda, and I hope to get through all of it. So I'll start off by with the IRTF notewell, which is pretty similar to the IETF notewell. If you're not familiar with it, you should read this carefully. At a high level, I will simply point out that you are simply following these IETF processes and policies by participating in terms of your the intellectual property of anything that you share. You are expected to file IPR disclosures on anything that you file that might have IPR that you're aware of. Otherwise, read the note for more details. Um, Generally, I will just point out one thing on the code of conduct. Please work respectfully. This is a group of people from many different backgrounds and many different with many different views. Be respectful and have respectful discussions. And finally, the goals of the IRTF, specifically pointing out that the IRTF conducts research and it is not a standards organization. So as you engage, as you participate, and as you discuss items, bear in mind that we are not trying to standardize anything here. And with that, let's get to the agenda. So basically, we have a number of things today. We're going to start with a different item than usual, which is source priority flow control in data centers from J.K. Lee, who's at Intel. And I will let him talk about this. This is different in the sense that we don't normally, or often anyways, talk about data center stuff. And we have sometimes done that. And we have a presentation here which seems to be very much on target for ICCRG. So we're going to talk about that first. After that, it's going to be more things that you are used to. We're going to start off with, we're going to go on to a CCID for BVR for DCCP, followed by a presentation from Ayush Mishra on the game theory behind running Cubic and DVR. You've seen Ayush in the past at ICCRG, and I'm looking forward to this presentation. And then we have updates on BBR V2 from Praveen and Neil and Ian. And Praveen's also going to give us an update on RLIT back. So with that, I'm going to get started. JK, are you here?
Yes, hi, Anna.
Oh, there you go. Wonderful. So you can, for all the speakers, you can present your own slides. You just have to go to the little start slides share button, which is right next to the hand, the raised hand thing on the left. There we go. And I will allow you to do that, which you should now be able to. Hang on, I'm trying to grant. Where to stop sharing first, perhaps. Ah, and now you share screen should be.
Okay, I'm in.
Excellent. The floor is yours, JK.
Yep, thank you very much, everyone. I'm JK Lee, principal engineer from Intel. This is my first time attending IETF, so um, I'm glad to be part of this forum. I'm gonna talk a little bit about source flow control, or a little bit more degenerate form, which is source priority flow control, source PFC. And this has been a collaboration mostly between Intel, and recently we started to talk about this at IEEE with Paul Condon and then Lily from Huawei. Oh, sorry, I need to click here. Good. So I don't think I need to go through what kind of conditions are there in data center. There are multiple different types, but one type we are looking at right now is in-cache congestion, which is mostly caused by the many-to-one traffic pattern. And it mostly happens at the last of switches, the last of first or second hop switches. And it drastically affects the tail latency because of the large queuing delay, or even it can cause packet drops. And absolutely, this tail latency is well known to have a large impact on the application performance or scale metrics. And especially when in-cache happens due to the line rate RDMA senders, because they are really starting to send at the line rate, or the messages and connections. The same size of message can actually finish really short amount of time, which means that it doesn't really give large RTT time for the congestion control to detect and then converge and react to the congestion. So fast reaction, possibly at the sub RTT time, is more preferable with RDMA in-cache in data center. Okay. So yeah, obviously for congestion, the community has been working on end-to-end congestion control for many decades. And at high level, yeah, it's end-to-end signaling from forward direction data packets and echoed by the receiver, so that the sender can adjust its transmission rates and congestion window. And one thing we kind of notice here is that the congestion signaling itself is carried by the data packets, either explicit congestion notification like ECN, or RTT measurement. So they happen to be coupled with ongoing congestion. And if, for example, there's a new sender arriving at the tail of the heavily congested queue, then the first packet of this new flow has to wait until all the other congested packets dequeued out, and then finally hit the receiver, and then can be echoed back. And also the nature of AIMD, or the typical rate control mechanism, it takes multiple RTTs to actually flatten the curve. Like if the rate adjustment mechanism is cut rate by half upon the reaction or detection of congestion, that means that 16:1 in-cache will take another RTT for 8:1, 4:1, down to 1:1. And eventually we want to really cut the rate down to 0 if there's a heavy in-cache, so that we really flatten the curve. That means that many RTT times will be required. At the same time, there are a number of flow control mechanisms, mostly layer 2, and well known for IEEE PFC. And they are really meant to prevent congestion packet loss from the beginning by employing something like a X on X off low latency reaction mechanism that is guaranteed to be happening within 1 microsecond. Detection and reaction should happen within 1 microsecond as required by the standard. But it's a hop by hop flow control. So although it can actually avoid congestion packet drop from the beginning, it effectively slows down the fabric because of many of the head of line blockings happening at the inter-switch links. And it can actually back pressure from the congestion point to towards the upstream switches and towards the eventually to the senders. And it is well known that some operational side effects like a PFC storm and deadlocks can happen at the same time. So here, this presentation, we are going to kind of stress on the need for the new layer 3 flow control mechanism, which can give us immediate detection and reaction. And the layer, it's better to be layer 3 so that we can reach out across the data center. So this is the one slide summary of the our proposal. So the key idea is very simple. At the congested switch, we just first compute the minimum time required to drain that target incast queue, where you can expect is something like a expected surgeon time of the queue. And the signal packet is generated and carrying that information backwards for the incast senders. And there are two different ways for us to consume this information. The first one is the sender side top of rack switch can convert this layer 3 signaling packet back to standard PFC to directly pause the sender NIC queues. So we call it source PFC. Or the signal information can be forwarded back to senders, and then sender NIC hardware or host networking stack can directly consume that information and pause the source flow. And we call it source flow control, or SFC. With that, the next slide is about simple diagram depicting the behavior of source PFC. So what we are talking about here is that simple cartoon data center with 2 senders and 1 receiver. There's an incast happening. So typically when we enable PFC end-to-end, that means that the destination top of rack switch will create PFC priority flow control, and this will pause the upstream aggregation and core switch links. Instead of that, what we do here is that we assume some simple mechanism at the switch ingress, which can learn about the ongoing congestion at the switch egress. So even before when we forward the packets from ingress to egress, the ingress pipeline has some capability to generate a signaling packet back to the senders. And here for source PFC, we are assuming that actually implemented that the source side top of rack switch can simply convert this layer 3 signal packet to PFC frames so that it can immediately pause the incast senders. So entire detection and reaction can happen within sub-RTT time, where the RTT is congestion-free base RTT. And here, we are not really aiming to replace end-to-end congestion control. This is more about kind of emergency break or reaction to heavy incast, because we are not really pausing any of the inter-switch links. There is no head of line blocking happening between the inter-switch links, and no PFC side effects are expected. Of course, we can deploy this mechanism every switch in the data center, but from our simulations and test beds, top of rack switch only upgrades can actually give us most of the bang for the buck, because the incast mostly happens at the last of switch, and the signaling between these top of rack switches can still give us pretty good reaction to most of the heavy incast. Meanwhile, when the heavy congested queue is being drained, finally the end-to-end congestion signal will be received by the receiver and then echoed by the receiver back to sender. So here, the point here is that this source PFC reaction can be much faster than the heavy congestion control reaction to the heavy incast, when especially queue depth is pretty large. This is the very simple testbed experiments to show the benefit of source PFC. Here we have two switches and multiple senders and receivers. Senders on the right-hand side mostly, and the receiver on the senders on the left-hand side, receiver on the right-hand side. There are two in-cast flows happening at the same time. Here, the experiment is designed in a way such that the link between top of rack switch 1 and TOR2 will be head of line blocked mostly by the in-cast happening at the receiver 2 will PFC pause the uplinks port, and which will in effect create head of line blocking also for the flows of sender 1 to receiver 1. So this is all the RDMA write request. So first we measure the Q depths over time using some telemetry mechanism. And here we compare the Q depths between the two mechanisms. On the upper hand side, we have the case where PFC is enabled everywhere versus the lower hand side, we have a case with the remote PFC or source PFC enabled. And you can see that the Q depths at all the three congested links are pushed down to drastically with more than sometimes tens of order of magnitude difference. With that, you may wonder what would be the throughput performance. So this is the measurement of the flow completion time of this more than thousands of flows or RDMA write request. And yeah, we see that in the CDF of the flow completion time, the source PFC performs better than the traditional PFC. Here, we actually didn't enable ECN because it was not easy to find the good tuning of ECN and DCQCN. And actually, when we enabled DCQCN, we found that the tail latency was worse in case of PFC. So we just wanted to simply compare the operation between PFC and source PFC. So you may wonder what information we need to carry for this layer 3 signaling packet. So key idea is very simple. So we have some more detailed backup slide at the back, down the road, how we can convey these signaling informations in the IEEE 802.1 QCG, which is the draft. CIM here means that congestion isolation messaging. Excuse me. So in the source PFC mode, we just need to mostly swap the source and IP addresses of the data packet so that the newly generated, so when we generate the signaling packet, we can just swap the source IP from the data packet and then use them as the new source destination IP of the signaling packet. With that, the packet will be forwarded, signaling packet will be forwarded back to the sender, and we can still carry the original destination IP of the in-cast traffic. It can be optionally used to cache some of the post time at the sender side top of rack switch. I can talk about that more later. And we should also carry something like a DACP or VLAN PCP, whatever QoS priority information that is needed to identify the actual PFC priority queue to pause at the sender NIC. And most importantly, we carry the pause time duration or expected surgeon time. We should be the smaller or the equal than minimum drain time to reach the target Q depths. So here the target Q depths could be something like an ECN threshold or slightly above or lower than that. When we try with different values, they didn't really make big difference because our reaction was the SPFC reaction is really fast. And optionally, we can carry some additional congestion locator information like switch port QIDs, but that's really optional. Even without that information, the entire protocol behavior should be the same. The additional information can help if you really want to consume that for more network-wide monitoring and then traffic management, etc. But that's a kind of beyond scope of the initial use case. And for the source flow control, we want it to be consumed by the sender side transport layer. So we need to carry some additional layer 4 port or maybe QPID like information so that the actual sender side flow and connection can be identified, which flow and connection to be paused as a reaction of this signaling. So when we look at this source flow control, bit more kind of advanced version of source PFC, because we are pausing the flow at the flow level, at the transport. You may wonder how does it look different from something like ICMP source quench? So just as a data point, there was actually a recent paper at NSDI this year, something called on-ramp, which also implements such a similar flow level, connection level flow control mechanism implemented at the Linux QDisk. So yeah, in order to make a reaction and consumption of this information, we need some changes on the software stack, or we need to modify the RDMA hardware stack. And there's one example in the NSDA paper. Back to this question, how does it differ from source quench, which is actually deprecated RFC, I think more than 10 years ago. As I understand, there are multiple reasons why source quench has been deprecated. First, it didn't really specify which information to carry or how to consume and react to that information at the sender side. And so we, in SFC or SPFC, we clearly specify that we just carry the pause time duration or the drain time duration. And we promote that the immediate flow control so that in-cast senders can really stop sending immediately rather than AIMD style of condition control, especially for data center. And yeah, source quench was really designed for or promoted for when internet congestion handling, but we are promoting this SFC for data center with single administrative domain. And in case of layer 2 data center, there has been something called IEEE QCN. It's actually quite similar in a way such that it also promotes the back to sender signaling from switches to the traffic senders. But this is a layer 2 congestion control with similar AIMD, still requiring multiple RTT time to flatten the curve. And Rocky DCQCN is a L3 adoption of QCN. Hope this answers one of the questions. And some additional questions are shared by the IEEE community by separate emails. So at high level, how do we secure the protocol? We assume this will be for single domain data center with trusted switching devices. And I can make some argument that the signaling between switches for source PFC could be similar to LLDP and BGP. And then I understand that there is a BGP encryption mechanism, but in reality, it hasn't been really used for many regions. It cannot really serve the problem of malicious or poorly implemented router, and it can actually cause additional headaches. So as I understand, no one not really heavily turned on the BGP encryption mechanism is. And for the signaling for SFC source flow control for the sender transport to react, we can see that this is quite similar to ECM marking, where the data center switches or intermediate switches and routers are provide some information in the actual data packet and consumed by the sender side transport. Here we are generating the new signaling packet instead of modifying or marking on the in-band data packets, but in a way such that the information is provided by the switches and then directly consumed by the end host is pretty similar in my opinion. And then ECN has been heavily used in data centers these days, something like a DC-TCP. At the end, we can simply implement Ccrg at the domain boundaries like a top of rack switches or maybe gateway switches, so that this new form of signal packet cannot really come from the outside of the domain. And another question was, yeah, is it only for Rocky? Yes, RDMA is a primary use case, and then Rocky V2 is the most popular transport of today, but we see more new type of transport for RDMA or RMA mechanisms are rising, and so we believe we can have many different RDMA transports in a similar way to scale on standard Ethernet fabric. And we have some argument how this can be a good fit for the machine learning training in the backup slide. So if you want, you can take a look. And SFC can also be applied to non-RDMA use cases, as similar to on-ramp paper from NSDI. And we are currently performing some evaluations with the TCP traffic. You may wonder that the edge-to-edge signaling is still sub-RTT, but it can be still proportional to the network RTT if the network size grows. So then isn't it too slow? So we have a simple mechanism that we can cache the pause time per destination IP at the sender side top of rack switch. And this information can be used to instantly pause another senders coming from the same connected, same switches, and then gearing for the same destination IP can be immediately paused without waiting for them to reach out to the sender side, receiver side TOR and then echo back. With that, this is a simple history of the mechanism. Yeah, we first talked about this idea starting from last year, April, and there are a number of presentations at the public domain and also recently more in the IEEE. Yeah, there is a suggestion that IETF should be aware of this activity, so we are having this conversation here in Ccrg. Thanks for the opportunity. And the plan at the IEEE is simply extending the existing 802.1 QCG condition isolation mechanism. It already has a layer 3 mechanism, so we can simply extend it to enable something like a source PFC. But I can easily imagine that if you really want to do source flow control for the transport to make use of this information, then IETF can be a better forum to discuss. Yeah, I think for the sake of time, I'm going to stop here, and then I can take some questions. Should I stop sharing my screen?
Hey, JK, let's keep your screen on in case people have questions about any other slides. We have a few minutes for questions.
There's a question from Jonathan still in the chat room, if I understand correctly.
Yep, go ahead.
But
Take that, and then Praveen can go on after that.
I was just pointing out that the basic multiplicative decrease mechanism is an auto log n mechanism. So that was from quite early in your presentation.
I see. Yes. Sorry if I misunderstood. But yeah, it still takes more than one ITT. I guess that's the key question. Yeah. Thanks for pointing out.
Praveen, you're up.
Question. So there was another work recently presented in Ccrg called HPCC. Can you compare and contrast the approach with HPCC?
Yes, HPCC, I'm also part of that effort. It's still forward direction signaling. So HPCC, you can imagine this as a really multi-bit ECN. So instead of just one bit ECN, it carries the multi-bit information about the condition like Q depths and then link utilization, but still in the forward direction data packet and echoed back by the receiver back to sender. So it still kind of suffer from, excuse me, the congestion signaling path is coupled with the ongoing congestion. So we do have actually simulation results demonstrating the effectiveness of source flow control or SFC with HPCC. So when the in-case ratio is not that small, then new congestion control like HPCC can actually do decently better. But here in this case, we actually created an in-case a little bit higher than usual. Let me go back. 88% of traffic is in-case burst with 122 down to 1. So it might be a little bit kind of severe in-case congestion. In those cases, then we still kind of generate up to orders of magnitude, and it's one order of the magnitude better improved flow compression time compared to SFC. And we could also maintain the buffer occupancy smaller and then slight improvement in the throughput. But overall, because of the queuing is better managed, that leads to the reduction of the flow compression time. Hope this answers your question.
Tianji, you're on.
Yeah, can you hear me? Just want to double check. Hello?
Hello.
Yes, okay. Hey, John, I have a particular question regarding your slide 6, the example. Normally in data center for the TOR switch or for the other aggregation switch, from the downlink to the uplink, you're going to have some ratio, not just like the one you're showing in the slide 6, like the downlink at 100 gig and the uplink is also 100 gig. Normally just like a 4:1 ratio. It's like not so congested as you're showing here. So like you are using 100 gig for the downlink, you probably are going to use like 400 gig or even combine up to 1 T. So in that case, are you still seeing so much improvement from your experiment? Thank you.
Yeah, that's a fair question. Thanks. Yeah, this has been intentionally designed. The topology has been intentionally designed to just nail down on the head of line blocking issue. And when we simulated the larger scale simulation for example, 320 servers, we definitely create a full bisection bandwidth topology without any oversubscription. And there we could still see that pretty good flow compression time improvement, even for the DCQCM, which is the actually improved DCQCM, also HPCC. And there was another presentation from at IEEE. So if you, sorry, yeah, this particular highlighted link, if you can click on this one, this was the measurement study done by Huawei a month after our initial presentation at IEEE, and then they actually quickly did prototype and then demonstrated when their RDMA traffic is mixed with TCP with, I think, no oversubscription or maybe small oversubscription, the benefit was still pretty good there in terms of tail latency. So yeah, but quick answer is that yeah, there are multiple data points that it can still help.
Sure, thank you.
Thank you.
All right, I have a question from the queue, from the floor. So I'll ask you this question, JK. I'm familiar with some work in the past, and this is probably a few years ago. Timely and from Google folks did some work on basically using RTD as a congestion signal for within data centers, and it was, if I remember correctly, they did some work on RDMA fabric. Have you compared your work to theirs, or have you looked at that work? Somebody else from Google might be able to shed more light on the specifics of the proposal, but have you had a chance to look at that?
Yes, yes. We are very well aware of such a new congestion control algorithms designed for RDMA. So HPCC is one of them, timely and recently Swift. I think Neil Carver is here today. And many of them really make a way more better congestion control than something like a DCQC or DCTCP because it's really designed for low latency, high bandwidth. But I think the fundamental difference is that incast can still happen because you cannot really perfectly synchronize all the senders, especially with RDMA, each sender is blasting at line rate. If somehow they happen to collapse within 1 or 2 RTT time, maybe more than just 3 or 4 senders, they can easily just fill up the queue very quickly. Right? And the end-to-end congestion control still has to kind of have the signal passing through the congested queue and reaching the receiver and echoed back. So this will naturally take at least more than 2 to 3 or maybe more RTTs, depending on the level of incast. So this source flow control, or we call it just back to sender signaling mechanism, provides that incast information directly back to sender within 1 RTT time. And so that you can handle such a unintended synchronized incast, or it may also handle the case where the timely or the RDMA congestion control happen to coexist with non-compliant congestion control, or maybe when congestion control which has a way larger RTT time that wouldn't really react to this incast congestion control signaling within soon enough, so that the back to sender is really handle such different cases.
Understood. Well, thank you so much for that. And with that, I'm going to, we do not have any other folks and we need to move on to the next presentation. So thank you so much for your time, Jake, and your presentation. To the folks in the group, I'll say that this is work that's going to the IEEE. And if there's any feedback that you'd like to pass along, I think it would be welcome either on the research group mailing list or directly to JK. And with that, I am going to move to the next presentation. Natalie, I hope I'm saying your name right. I'm not sure.
Yes, I'm here. Hear me?
Yes, I can hear you. I'm going to ask you to request presentation.
Sure.
And you should be able to choose your slides now.
Yes.
Excellent.
Okay.
Take it away then. Yes.
Okay. So, good afternoon, everybody. My name is Natalie Romo, and I work for the Strategy and Technology Innovation at Deutsche Telekom. And today I'm going to give a short presentation about an implementation of the BBR congestion control algorithm for DCCP, which we have named Ccrg. So, first of all, the motivation to bring BBR to the DCCP protocol relies on the fact that right now for DCCP, there are only 3 congestion control algorithms standardized, and all of them are loss-based. So we thought about bringing BBR precisely because it is a non-loss-based CC algorithm. Apart from that, we also wanted to use BBR within the multipath DCCP protocol. That means to bring it into a multipath scenario where the latency difference among the paths is a key factor to achieve a good performance. And we thought that in this case, BBR might be useful. Last but not least, we all know that BBR has proven to have quite good results for TCP in terms of having a low latency, high bandwidth, and also avoiding problems like buffer bloating. So we wanted to verify whether all these characteristics also apply for DCCP. On that basis, we started the development of BBR version 1 for DCCP as CC85 within the Linux kernel. This implementation is available as open source, and of course, it is based on the existing implementation of BBR for TCP. However, the main difference between TCP and DCCP relies on the unreliable nature of DCCP, which means that all the functions related to the acknowledgement generation and their processing are part of the CCID definition, not of the protocol itself, which means they are going to be part of the CCID code. Apart from that, we also wanted to adopt this existing and mature TCP BBR as a new CCID profile for DCCP. And for that, we have already submitted an initial draft, and we will be happy to receive some feedback and comments about it. So once we finish our first implementation of BBR for DCCP, we started some evaluation in a controlled environment using a single path and a multi-path scenario. In this evaluation, we compared the performance of our implementation of BBR, which is CCID5, with the performance of CCID2, which is the default congestion control for DCCP. The results show that for both cases, for single path and multi-path, CCID5, that means BBR, has way better results in terms of latency when the path has a limitation in the bandwidth. Apart from that, in the case of the multi-path scenario, CCID5 also helped to improve the scheduling performance. Moreover, the main achievement of this test was to prove that the conceptual basis of TCP BBR was also applicable for DCCP, which means that all the existing studies and results available can be extended to DCCP as well. The whole analysis and also the description of the test environment is here in this paper, which I have linked in case anyone is interested to check about it. So after executing this first test, we moved to a more realistic environment, and we started testing our implementation in an LTE link, and we compared the result of CCID5 and the standard TCP BBR. In these results, we found that during the probe RTT phase, the drops in the bandwidth were quite deeper for the CCID5 in comparison with the TCP BBR. And also the duration of the probe RTT phase was a little bit longer in some cases in comparison with TCP. So we started an analysis of this problem, and we figured out that what was the cause. The point is BBR requires the restoration of the congestion window when it leaves the probe RTT phase. So it restores the congestion window from a quite low value to the value it had previous entering this phase. Apart from that, the DCCP requires that when there is a big change in the congestion window, there has to be a synchronization between the sequence and the acknowledgement validity windows. This synchronization uses a feature negotiation function, which is described here in this figure. Basically, the sender starts this negotiation, and once it receives the confirmation, it can update the local value. This brings us to a problem, and is that the probe RTT phase duration acquires a latency dependency, because this negotiation takes at least one RTT before we can update the local values and proceed to the restoration of the congestion window when leaving the probe RTT phase. So to solve this problem, we applied a temporary solution, which is that we trigger this synchronization, but we don't wait for the confirmation to update the local values. That means as soon as we trigger the synchronization, we can update the local value and proceed to restore the congestion window. After applying this temporary solution, we managed to achieve a similar performance comparing CCID5 and TCP BBR. Now, the question is that, as I said, this is a temporary solution, and we would like to start a discussion to know what is the best approach to solve this problem. So maybe a new or an enhanced feature for the sequence window negotiation is necessary, or maybe there can be a different approach that helps us to solve this problem. So to summarize this whole thing, we have implemented BBR for DCCP. The initial tests that we have made have proven that the conceptual basis of TCP BBR applies as well for DCCP. Of course, taking into account the unreliable nature of DCCP and the difference that brings us. And on that basis, we would like to adopt BBR as a new CCID profile. For that, as I said, we have already submitted an initial draft. We submitted it initially to ICCRG, but we have been told that this has to actually be part of the TSBWG group. So in the further version, we will submit it there. But we will be happy to receive any comment or any feedback about it. The second question comes about this sequence window negotiation. So we have described the problem and we would like to receive some feedback about it and to start as well a discussion there. But we are not sure where should be the right place to start a discussion, either here in ICCRG or in TSBWG. So that's the reason why I'm making this presentation now. And that's it for now.
Thank you, Natali. That was a wonderful and short presentation. So, and thank you for that last slide in particular. I think it's Gauri's in the queue, so I'll let him have a take as TSBWG chair. Go for it, Gauri.
That we'd be able to discuss this on the mailing list and make some progress with the algorithm and the proposal. I'm not sure where the home would be, but it lies between these two groups. And whatever the home, you shouldn't be discouraged. Please discuss how to fix it, and please discuss the issues. It was a great presentation. I don't know what the outcome will be, so I'm looking forward to hearing more from you about these methods.
Okay, I will do so. Thanks.
Thank you, Gauri. Praveen, you're up.
I had one question here. So you refer to BBR here as mature, right? My understanding is there's quite a few presentations today talking about BBR v2, which is the next evolution of BBR with like better coexistence with cubic, etc. Right? So my question is, if you're going to create a new standard, would it be better to wait for BBR v2 to mature before doing this? I guess that's my question to the group.
Yes, I mean, from my point of view, we are also planning to implement BBR version 2 and test it in DCCP. That is in our scope of work for next year. And I think, yes, it would be better to use BBR version 2 as it is a more mature version.
All right, so we're going to take more discussion onto the list. And when I say the list, I mean ICCRG, but we are going to talk to the chairs about, oh, I see the AD is in there. So Martin, go for it.
Well, not the AD for this, but yeah, I support this work as well, but I am a little concerned that this is racing a little bit ahead of the actual TCP BBR work, which I think probably has a little more data to support it. So, I mean, it seems like most BBR discussion at this point is happening in ICCRG. And you can certainly do a draft in ICCRG. It would be experimental, but given the BB, we'll find out more, I guess, in a minute here. But given the BBR is still a little, is a moving target, maybe that's the right designation for now.
Yeah, that's my sense as well. But we'll take this discussion offline with the chairs of TSBWG, and we'll get back on that. David, you'll have the last comment, and then I'll have to move on to the next discussion.
Discussion among chairs is fine. I think ICC, as has been noted earlier, I think ICCRG is the right place to discuss the technology, and is also the right place to figure out appropriate timing. When the timing is appropriate, TSBWG is almost certainly the venue to work on the draft and standardization, but need to get the timing right and make sure that it's well coordinated with BBR as a whole.
Yep. Thank you for that comment, David. All right, thank you so much, Natali, and I hope to see you on the mailing list.
Okay.
And people, please engage. It's good to have this mapping for BCCP as well. I will now move on to the next presentation, and that is Ayush. Ayush, are you here? I see you up there. Can you? I see you requested. I'm. A minute. All right, take it away, Ayush.
Okay, so yeah, hi everyone. I'm Ayush. I'm a third-year PhD student at the National University of Singapore, and today I'll be talking about some very interesting work that we've been doing on studying the game theory behind actually, choosing between running Cubic and BBR on the internet. This work has been done in collaboration with my collaborators, Jingxi, Melodies, Sean, Raj, and my advisor, Ben Liao. Okay. So since BBR was introduced in 2016, a lot of websites have made the performance-driven decision to actually adopt it and use it to send data for their websites. And companies like Google and Spotify and Dropbox have reported seeing lower delays and better throughput, especially in lossy networks where ACK-locked, loss-based algorithms like Cubic are known to suffer. And clearly this trend has caught on. Since we did a measurement study in late 2019, we found that close to 18% of the Alexa top 20,000 websites are already running BBR. And this 18% metric actually goes up even more when you consider the more popular websites or websites that contribute more to downstream traffic, like for example, video streaming websites. So the question we want to ask is, where is this transition really heading? So this transition in the internet's congestion control landscape is definitely not a new thing. We've seen in the past that a Renault-dominated internet in the early 2000s slowly transitioned into an internet that was mainly Cubic dominant. And much like BBR does today, even back then, Cubic basically gave you better throughput and better utilization guarantees on the internet, which is why people moved on to it. But there is one key aspect in terms of which this transition from Cubic to BBR is very different from the transition that we've already seen, which was between Renault to Cubic. So the transition between Renault to Cubic was essentially between two window-based, loss-based algorithms. So they both had the same congestion control philosophy. They both reacted to the same congestion signal, and that's why we didn't really face a lot of problems. But right now, as you have more and more websites using BBR to replace their existing loss-based algorithms, what's that actually doing is it's creating a paradigm shift in how congestion control is done on the internet. Now we have websites, now we have flows that are competing with other flows, and we have all mixed set of congestion signals that everyone's responding to. So the question we want to ask is, given this performance improvement that BBR has given us so far, where do we actually expect this transition to move? Or in other words, if we're seeing such good performance benefits, is it reasonable to expect everyone to switch from Cubic to BBR at some point in the future? So this is a question that we discussed in a recent short paper at APNet 21. Was titled Conjecture, Existence of Nash Equilibria and Modern Internet Congestion Control. And the main insight we found while writing this paper is that you can really model this entire problem of choosing between Cubic and BBR as a normal form game, because we have some players, or in this case websites, that can maximize some utility, which in this case is network performance. And all these players have a fixed set of strategies, which is either running Cubic or BBR, available to them to maximize their utility. So the approach we had to analyze this entire system was actually to calculate the Nash equilibrium in the network, where the senders have the freedom to choose between cubic and BBR to maximize the throughput. So just as a refresher, a Nash equilibrium is basically a strategy distribution where none of the players have the incentive to switch to the other strategy. Or in other words, in networking terms, it would mean a distribution of congestion control algorithms over the network where none of the senders have the incentive, have the performance incentive to switch from cubic to BBR or vice versa. So let's look at the example on the slide here. Let's say we have a network with 7 senders, and of the 7 senders, 4 of them are running BBR and 3 of them are running cubic. And given this network configuration and congestion control algorithm distribution, each of the flows are getting some share of the bottleneck bandwidth. Now let's say one of these senders, Alex, decides to switch from BBR to cubic. And while making the switch, he essentially changes the internet's congestion control landscape, and now he sees different throughput on the network. So in this case, we're going to make the assumption that when Alex does this switch, if he sees a better throughput, he's going to switch to the algorithm that is giving him better throughput. Or basically, all the agents in our network are going to make a performance-driven decision on which algorithm they want to run. So in such a network, if we are able to find a congestion control distribution where for everyone making the switch to the other algorithm gives them strictly worse performance, that essentially means that this congestion control algorithm distribution is the Nash equilibrium for that network. Or basically, this is the fixed share of cubic and BBR flows we have in the network. There's really no incentive for the number of BBR flows to increase or for the number of cubic flows to increase. Now, a conjecture in the paper is that we think this Nash equilibria will exist in all kinds of networks where you have senders and senders running cubic and BBR flows. And this is actually quite a big claim to make, which is why we still say that it's a conjecture. But we have good reason for making this conjecture. So in the paper, we go over the exact observations that we made based on how cubic and BBR interact and how these observations actually guide us towards making this conjecture. But in the interest of time, I'm only going to discuss the key observation over here, which will hopefully convince you guys that, yeah, there might indeed be a Nash equilibrium when, n number of flows compete at a common bottleneck. So over here, I'm going to plot a graph for a system where, let's say we have symmetric senders. So all my senders have the same RTT, and they only differ in the sense of which congestion control algorithm they choose to run. Now, we know from other measurement studies that when you have a very small number of BBR flows in the network, they can get a disproportionately high share of the bottleneck bandwidth. So I'm going to plot this as point A in the graph on the slide. So on this graph, basically on the y-axis, I have the combined throughput of all the BBR flows. And on the x-axis, I have the percentage of BBR flows in each congestion control algorithm distribution. So we can plot point A based on the observation made by other measurement studies. We can also plot point B, which basically says that when all the flows at the bottleneck are BBR flows, they will basically use the entire bottleneck bandwidth, which is really a no-brainer. So we have 2 points, point A and point B, and we can also say that all the data points between point A and point B will lie on some line connecting the 2 points. And these different possible lines I've just depicted using the different gray squiggly lines on the slide. So the interesting thing about this graph is that when you actually plot out these values, every point at which your gray line intersects the fair share line, that essentially signifies the Nash equilibrium point in the network. So the fair share line, I'm sorry I didn't go over it earlier, but the fair share line is basically the line at which all your flows get the fair share. So if BBR was getting the fair share in this network, the data points would follow the fair share line. So let me actually go over why we actually claim that this intersection point in this graph is going to be the Nash equilibrium. So to do so, let's zoom into one of these intersection points. So at this intersection point, basically what's happening is that the average bandwidth of all the cubic flows equals to the average bandwidth of all the BBR flows, which is why neither of them wants to switch to the other kind. But why do we say that this is actually the Nash equilibrium? Well, we say this intersection point is the Nash equilibrium because let's say we move to the right of this point, which would signify that a cubic flow in my current configuration wants to switch to running BBR. So when we do this, we will actually be transforming the entire system into a regime where BBR flows perform worse. On the other hand, if there's a BBR flow in the network that wants to switch to cubic, that would move the distribution to the left into a regime where cubic flows perform worse. So in both cases, the cubic flow does not switch to BBR because that would mean moving to a region where BBR performs worse. And similarly, the BBR flow does not want to switch to cubic because that would mean moving to a regime where cubic flows perform worse. And because there is no incentive for any flow to switch to the other strategy at this intersection point, this by definition becomes our Nash equilibrium point. Now, the graph that I plotted earlier was theoretical, but we have validated these predictions through actual experiments. So we had 20 flows running through different link speeds and different buffer sizes. And across these different regimes, we plotted the normalized bandwidth for BBR. And we did actually observe that at the intersection point where the line crosses the fair share line, to the right, BBR actually performs worse than cubic, and to the left, cubic performs worse than BBR. So in the paper, beyond the observations, we also use these observations to write down a couple of equations, which we use to come up with the exhaustive proof for showing that a Nash equilibrium will always exist when two flows are competing, and the two flows have the choice to run either cubic or BBR. But in the interest of time, I will not go into the details of this proof. But I will just say that the Nash equilibria in this case depends on the buffer size, unsurprisingly, and the Nash equilibria also exists independent of the fact whether your two flows have similar RTTs or distinct RTTs. But beyond the exhaustive proof, we also wanted to empirically validate some of the claims of our conjecture, which is saying that the Nash equilibrium will always exist. So what we did was we set up networks with 6, 9, and 12 flows, where all these flows shared a common bottleneck bandwidth. And in each experiment, exactly 1/3 of these flows had 20, 50, and 80 ms RTTs. And this was basically to simulate flows of different RTTs competing with each other. And then we wanted to see how this actually impacts the existence of the Nash equilibrium. So given this network configuration, we basically ran all the 2 power n combinations of different flows running cubic or BBR, and then we recorded their throughput. And once we had their throughputs, we used these throughput values to validate if any of those congestion control algorithm distributions were the Nash equilibria. So just to recap, if we have a 3-flow system and we say that CBC, or the first flow running cubic, the second flow running BBR, and the third flow running cubic again, is the Nash equilibrium, that basically means that when your distribution is BBC, the first flow gets worse throughput. When your distribution is CCC, the second flow gets worse throughput. And when your distribution is CBB, the third flow will get worse throughput. So before I actually get into the graphs, there were a couple of interesting properties that we found while actually calculating this Nash equilibria in our experiments. Interestingly enough, we found out that in all our experiments, there was exactly one Nash equilibria. So there was one fixed distribution of congestion control algorithms where none of the flows had the incentive to switch to the other algorithm. And we also found that in each of these Nash equilibria, the congestion control algorithm distribution fell in such a manner that it was always the smaller RTT flows that chose cubic, and the larger RTT flows decided to opt for BBR. So later on in the graphs, when I say that, let's say there a 6-flow system has a Nash equilibria where 50% of the flows are running cubic, that basically means that 220 ms flows and 150 ms flow is running cubic, and 150 ms flow and 280 ms flows are running BBR. So while actually calculating the Nash equilibria, we experimented with different link speeds and different buffer sizes. And the entire point of this was to see how the link speed and the buffer sizes impacted where the Nash equilibria lied. Predictably, buffer size had the biggest impact on the distribution at the Nash equilibria. So when your buffer size was deeper, you're more likely to have flows opting for cubic rather than your buffer size when your buffer size is shallower. And this makes sense because cubic is a buffer filling algorithm and it's likely to be more aggressive when you have deeper buffers. We also tried changing the RTT distribution to see if that made any impact on where we earlier saw the Nash equilibria. And we found that there was very little impact on what the distribution of algorithms actually was at the Nash equilibrium point. So to summarize the findings of our short paper is that despite BBR's current throughput benefits, we think it's unlikely that cubic is going to disappear soon. And this is because we think that BBR's performance benefits that we're seeing on the internet today are going to wane as more and more people on the internet start running BBR. Therefore, we think that the internet is likely to remain a heterogeneous mix of congestion control algorithms. We also think that a lot of our results are a good lesson in understanding that TCP performance is highly contextual. So how your algorithm performs not only depends on the characteristics of your network, but also who you're competing with. And lastly, I would like to note that we can make all the fancy predictions of having different kind of Nash equilibria, but the internet actually does not follow economic game theory exactly. So it's not a given that the internet will move towards Nash equilibria, but given the fact that a lot of people on the internet are likely to make the decision between cubic and BBR based on performance, we think it's likely that even if we don't reach the Nash equilibrium, we are going to move in that direction. Now, obviously, there's a lot of future work to be done in this paper. We want to come up with a formal proof for general n-flow game. We also want to look at the effect of more complex network utilities. So in our paper, we assumed a very simple utility function where every flow wanted to maximize its throughput. But obviously, that's not true on a real network. Flows are likely to care about both throughput and delay, and the utility function is likely to be a combination of these metrics. We also want to look at the effects on the congestion control algorithm distribution at the Nash equilibria in the presence of BBR-V2, multi-hop paths, and EQMs, and also how things change when we have very, very deep buffers and much larger number of flows. So in terms of very deep buffers and much larger number of flows, we have been doing a fair number of experiments. And so far what we found is that the trend still exists, that at higher BDPs, the share of cubic flows at the Nash equilibria will be greater. But there is one aspect in which the large flow experiments differ from the experiments that we've done in the short paper. And that aspect is that when you have very deep buffers and very large number of flows, things are not as nice and clean as having one Nash equilibrium point. Generally, we found that there exists a region or a window within which you're likely to get a Nash equilibrium. Okay, so thank you for your time. That's all I have for you today, and I'd like to take questions if there are any now.
Thank you so much for your time, Ayush. This is a very, very interesting piece of work. A number of people in the queue already, but I'm going to ask a question before I get in there. Actually, two quick questions. One of them is that you seem to suggest CBB and BBC as two different experiments. And
yes.
That seems to suggest that the order in which flows entering choose makes a difference.
So it's not really the order in which the flows enter, but it's just the fact that we have given all the flows some cardinality, and we're treating all the flows separately. So basically, we are in this notation, we're not assuming that flows are symmetric, or there are a bunch of flows that have same RTTs. So each flow here is distinct. You can assume each flow has different RTT and therefore is a separate entity.
I see.
Yeah.
Okay, well, maybe I'll ask you later, but I can't see the difference then between the first setup there, or the first experiment, and the third one, because to me they seem to be the same.
Okay, so basically the first, second, and third flows might have different RTTs.
Understood.
Which is why BCC and CBC are different.
I understand. All right, I'm gonna get out and allow the others to ask questions, but I'm going to close the queue here because we don't have a lot of time. All right, go for it, Ian.
Hi, thanks. This is quite interesting. I do have some kind of extra complexity to add on to this whole thing, which kind of at least my thoughts on how this replicates or does not replicate the real world. So it's worth it noting that the most valuable flows are commonly the short ones that are very app-limited. The canonical example is things like search and ads. And in the case of my employer, generate a lot more value, certainly a lot more value per byte than something like a YouTube video. And given the amount of value, it's actually kind of incentive compatible to make sure your long-term flows are not too aggressive and that they move out of the way quickly when something that's high value, like search or ads, comes up.
Yeah.
And the other thing to note is it's not uncommon to have between 10 and 20 connections for a single page load on the internet. And when you're dealing with that kind of chaotic environment where nothing really gets out of startup or very rarely, it's very difficult to reason about the congestion control performance, right? Like the congestion avoidance phase is basically like irrelevant. You can largely like remove it from the congestion controller, and it would like largely work the same for search and a number of other major websites. It obviously matters intensely for YouTube. It matters intensely for, a large flow like an upload or download. But I guess even for a given provider, it might actually be incentive compatible to like make your congestion avoidance scheme not too aggressive to make sure that like smaller flows, which are higher value, like are favored. And so I think it's complicated.
Yeah.
So
yeah.
we did test to make sure that this was not a problem and make sure that there was no negative impact on search latency when we launched BVR originally. And we did a bunch of studies and couldn't find anything. So as an anecdotal.
Yeah. Yeah, I think all those are fair points, and I completely agree with you that this is an extremely complex problem. In fact, you mentioned the flow durations and how flows of different durations might have different metrics, and they might want to optimize for different things. So yeah, all those things definitely complicate things a lot. But currently, from what we are working on is the assumption that all your flows, that all the flows that you care about are substantially long, such that they enter congestion avoidance mode, and then we want to see how performance is going to change for these considerably longer flows.
Hi, Martin Duke. Thanks. This is very creative way of approaching the problem. But there's a little discussion in the chat because, of course, the term RTT is a little overloaded in our field, right? Where sometimes it includes the buffer, sometimes does not. So there are two ways to look at it. That if the two intuitions that we're applying in the chat. One is that that like if the path latency aside from buffering is low, the cubic is favored, and therefore like low latency paths will just use cubic forever. The other one is that as more and more people adopt cubic towards the Nash equilibrium, that buffer occupancy drops, and therefore that the benefit of adopting BBR instead of cubic lessens. And so the nth person to adopt cubic has no incentive because the other BBR people have already reduced the buffer occupancy. So I don't know if you can speak to either of those intuitions, if both or neither or one of them is correct in your view.
Yeah, so generally we have seen that there are diminishing returns in both directions. So whether it be for more and more people to adopt cubic or more and more people to adopt BBR. And we are in the process of actually coming up with a model that can reason about these diminishing returns. And I won't get into the details, but at a very high level, basically why we think this is happening is that when you have both cubic and BBR flows competing at the bottleneck, what they do is that they basically section off different regions of the buffer. So you have one box that belongs to BBR and one box that belongs to cubic. And as you put more and more flows into the cubic box or more and more flows in the BBR box, the boxes don't increase in size linearly compared to the number of flows you're putting into them, which is why we're getting diminishing returns, and which is why the rate of acceleration when you reach the Nash equilibrium point keeps on reducing in terms of the performance benefits that you'll get.
Neil, you're up.
Yeah, Neil Cardwell here. I just wanted to thank you first off for this work. It's really interesting and seems super useful. I just wanted to amplify some of the discussion here about the workload that's being tested here. I think a lot of us are thinking it would be really useful to, in future versions of this work, to include a sort of mix of short and long flows. And in particular, the kind of effect I'm interested in is that if you have a dynamic mix of entering short flows, then often every time somebody enters the bottleneck, they'll cause packet loss as they sort of try to figure out, what bandwidth and how much buffer space is available. And if those flow entries all cause packet loss and those flow entries are close enough together, then that can basically prevent cubic from reaching its fair share, because obviously it's going to be very sensitive to how far apart those loss points are. So I think you might get very different answers in the question of what CC is incentivized if there's sort of a mix of dynamically entering short flows. So I'd love to see that in a future version of this.
Yeah. So we're definitely considering different kind of workloads. I think it's a great suggestion that we should look at a mix of short flows and long flows and see how things are changing. In fact, another thing that we are exploring currently is if you remove, right now we were just experimenting with long flows, but we also want to experiment with what happens when you have video workloads. And when you're dealing with video workloads, ideally the utility function that we'll be looking at would not be the throughput, but actually the QoE that your client is calculating. So yeah, thank you for your suggestion. I mean, all these different aspects of the problem, I mean, we have been also trying to reason about it a lot. And in fact, the biggest problem we're facing right now is really, to come up with a nice systematic way to explore all the different things that can happen in this space.
Hey, great work. Hi. Hey, this is great work. So I'm assuming this work was done measuring BBRV1 with cubic. It would be also interesting to include BBRV2. The second comment I had was, yeah, you're right that the evolution here might not be just based on maximizing throughput as the utility function. So I think certainly reducing latency is one of the goals on the internet, right? So for all the players here, the utility function might not be just maximizing throughput. So that should be taken into account. And the other thing here is that uh, there's certainly a benefit to standardizing on one algorithm in the long term. So when you look at it from purely, engineering efficiency point of view, if there's one algorithm that can give you better throughput and lower latency, that's what everyone will eventually converge to.
Um, yeah, I agree. But actually, from a from a design point of view, I think it's quite a hard problem to convince everyone to switch to that Oracle algorithm just based on performance, because that would mean that okay, in this graph we basically want our designed algorithm to always exist north of the fair share line. And I mean, that you can obviously design based on whatever utility function is. You can design, a utility-based algorithm that only maximizes that utility. But yeah, I think it becomes a very hard problem to, um, incentivize people to switch, incentivize everyone to switch to just one algorithm, because there are different, because performance is contextual, and also because generally the performance gains are diminishing as more and more people use it. So from a design point of view, I definitely agree that the best thing is to have everyone on the internet run the same thing. But realistically, we feel that that's something that might never happen, and we might have to figure out a way to work around with these zoo of algorithms.
Thank you again, Ayush. We seem to not have scared you away, given that you came back and presented the second thing with us, and we look forward to seeing. I look forward to seeing more of this work. In particular, the last thing that you just said, which is to, I'd be very curious to see how you can, if you can extend this to the zoo of algorithms that you've found either on the internet. And with that, I'm going to move on to the next presentation. Thanks again, Ayush. And please, Ayush is on the ICCRG mailing list. So if you want to have any discussion on this, please take it there. I encourage that. I'm going to ask Praveen to come back on so that he can start his presentation next. Praveen, we are running behind, so I'm going to ask you if you could try to keep it tight.
Hello, everyone. So this talk is slightly different. I'm going to be talking about implementation experience, hopefully, talking about two drafts that have been presented to the ICCRG in some form. We have an implementation update on both of these algorithms. So a quick recap on RLEDBAT. So RLEDBAT is basically trying to bring the benefits of LEDBAT or LEDBAT++ to the receive side of the transport connection. The draft currently only talks about TCP, but it could be applicable to other transports. The key insight is to use the flow control mechanism to throttle the peer. In the TCP case, it's basically shrinking the TCP receive window and growing it based on running sort of an equivalent congestion control algorithm on the receiver side. I misspoke there when I said shrink. So yeah, we don't shrink the advertised window. We just reduce it by the amount of bytes we received, but we do tune the window over time depending on the observed events from the network, like loss. Why is this important? So one of the reasons why just a center-side congestion controller is not good enough in practice is because a lot of software uses CDNs. A lot of CDNs currently don't have, for example, LEDBAT++ support. It's harder to update all CDNs to have the right congestion controller. Proxies can prevent effective use of LEDBAT on the end-to-end path. So if you have proxies on the path, then effectively from the server side, you're not actually measuring the right bottleneck and are able to basically throttle your sending rate. And the receiver has very clear information about which download it thinks are background downloads compared to foreground downloads. So there's advantages logistically in doing it on the receiver side. And this work is based on this draft, which is currently active in ICCrg. So we did implement this in the Windows TCP stack. So we have a single API currently that enables both the sender and receiver side scavenger algorithm. So LEDBAT++ and RLEDBAT. Our implementation of RLEDBAT is based on LEDBAT++. So it includes all the additional mechanisms that were introduced in LEDBAT++, like using RTT measurements instead of one-way delay, slower than Reno congestion window increase with the adaptive factor, as well as the multiplicative congestion window decrease with the adaptive reduction factor. The slow start is also modified to be slower than Reno. And then we have the periodic slowdown. So we did simplify this compared to LEDBAT++. So we currently are doing one slowdown period per base delay measurement interval. So this was deliberately done to simplify the code. We haven't compared one approach to the other, but this just is a simpler implementation. And we also simplified the base delay implementation based on the RLEDBAT draft. So we do require negotiation of timestamps. So what this means is that if the application did request RLEDBAT, the timestamp negotiation may fail with the server. In that case, we need to reflect that up to the application so it can implement its own fallback logic to throttle, for example, using a fixed rate. Currently, we don't take an action if a data packet is received without timestamps after establishment. So if, for example, a middle box is stripping timestamp options, we are currently not reacting to that. That's actually the standard says, the receiver should drop those packets, but we currently don't. This is an area where we would like to continue some investigation to see what the draft should recommend. But we are collecting data on this to see how prevalent this is in the wild. The other problem that we haven't mitigated is that the RTTs measured could be inflated because of bursts during slow start on the sender side. There's no effective mitigation we can think of this on the receive side. If there are, this might be an area of research. So one of the things we observed while we started experimenting with this in production was to find that there are several CDNs which currently do not enable timestamps. So we worked with many CDNs to enable timestamps when the client requests timestamps, and I think the coverage is much higher now. We are currently doing these measurements with the Windows Update downloads, both for operating system updates as well as store downloads. And we are aiming to share some data by the next ICCrg. I'm leaving a question open here. I'm a co-author on the RLEDBAT draft. This presentation was about the implementation, but now that we have an implementation based on the draft, I wanted to ask Jana and the group whether we should consider publishing drafts as experimental. We can take that during the Q&A. I will go on ahead with the presentation because we have limited time. So I'm also going to talk about BBRV2 and our implementation of BBRV2. So BBRV2, a quick recap, is a model-based congestion control algorithm. The goal is low queue occupancy at the bottleneck buffer, low loss, and also some form of bounded Reno and cubic coexistence. So the way the algorithm works is continuously measure bandwidth, round trip time, packet loss, and then ECN markings from the network, and basically figure out a rate that the sender should be sending packets at. There are some notable additions in V2 compared to V1. So the bandwidth probing timescale is adaptive. Loss and ECN have been incorporated into the network model. And then even when we are application limited, we want to basically adapt to loss and ECN information. And finally, because there is significant ACK aggregation in networks, we want to adapt this event based on estimating the amount of ACK aggregation that's happening in the network. And finally, the computed rate, the sender will basically paste the packets at the computed rate. So a brief overview of how we implemented this. So basically, the code is actually open source. It's available at this link. So that's what we based our implementation on. We integrated it as a congestion control module in the Windows TCP stack. It's currently available as an experimental knob in Windows 11 insider builds. The rate-based pacer was built into TCP, so we're not using a pacer that's outside the TCP module. And the way this works is that basically on each send, we're computing an allowance based on the time since the last send. And effectively, if the allowance does not allow us to send the packets at that time, we schedule the pacing timer to send the remaining data. So one of the challenges for us was because this code is also integrated into the Linux kernel, one of the challenges was that, and because the code is not final, it's still evolving, we wanted to integrate this, but still leave most of the code intact so that we can enable direct comparisons between, future versions and be able to, pull in those changes easily. One of the simplifications we did was we currently don't do any ECN handling. So we currently assume there's no ECN marking happening on the network. So that's just a simplification, but eventually we'd like to add that in. I would like to say that this sort of, we called it a reverse engineering approach, basically just looking at code and trying to implement a congestion control algorithm is something we've done for the first time, and it was very, very hard. Lack of spec was a significant problem for us while developing this. But thankfully, we had good support from Neil and Yuchang on email, and we were able to get most of our questions answered. But longer term, it's probably not sustainable. Some of the early data. So significant improvements in latency. So particularly Cubic, we see latency overshoot a lot beyond the base RTT. But in this case, we're seeing up to like 10x improvements in many cases, and some throughput improvements as well. And these are like test cases in the lab that are doing wide area network emulation. So one of the interesting things was, hey, this is primarily aimed to reduce latency. Let's run it at ultra low latency test cases where you have like back-to-back systems in the same rack and loopback test cases, and we see that there's actually a CPU usage bottleneck. So the algorithm is executing more cycles compared to Cubic. So this is something we would like to address by doing software optimizations. And we also find that there are interactions between pacing and LSO. LSO is basically, a TSO, or like sending a large segment out to the NIC to improve the efficiency. And we find that because of pacing, there are fewer opportunities to do so, and the size of the LSO is actually smaller. We also did an inter-region test in the Azure cloud, and we see about 20% throughput improvement and not much difference in latency. This is a low loss sort of not oversaturated network basically. So there's ample headroom, and we see basically throughput improvements, but not much difference in latency in this particular test case. Significant fairness issues still. So in all our lab tests, we see that Cubic dominates BBR-V2 across a range of test cases. So I think in BBR-V1, we sort of had an opposite problem with some of the shell buffer cases, but in this case, we find that I think maybe we have overcompensated a little bit, and Cubic is dominating BBR-V2. And currently, it doesn't seem incrementally deployable. Of course, if you have a network and workload where you can guarantee that it's only going to be BBR-V2, then it's certainly deployable. But otherwise, for any sort of incremental deployment, currently we have significant fairness issues. So next steps here. So Neil did promise he'll bring a draft. I think his talk is next, so I'm looking forward to that. But basically, we would like to help review that draft and adopt it and take it forward and change our implementation according to the community feedback. We'd like to resolve the fairness issues when Cubic shares the bottleneck link. And of course, the CPU usage optimizations that need to be looked at, and finally, deploy and measure in production. A big shout out and thanks to Neil and Yucheng for all their help on this work. Questions?
Thanks so much, Praveen. I want to say we don't have time for questions. There is negative time for questions, but if you have a really quick question ask here, or I would recommend that you take it to the chat if you can, because we're already way behind on time. Vidhi, do you have a burning question that you want to ask in person?
Not really, just a very quick comment. So about our LightPad and LightPad Plus was the gain factor and the target. Those are the two things I just wanted to say that we shipped these two last year in our TCP implementation, and the gain factor that we are using and the target. We probably played with it a little bit because it wasn't working. The additive increase wasn't going as fast as I was expecting, and the throughput was really suffering. So that's all I want to mention, and maybe I can speak to Praveen offline.
Yes, and I would encourage, by the way, I would encourage even for conversations, I would strongly encourage using ICCRG as a place where when you're having conversation across on clarification of implementations or various things, if you're able to have it on ICCRG, a lot of good things come out of it because the community gets to see it. There's a record of it. It's available for others to see later when they're doing the implementation work. So not just for this, but for Praveen and Neil, when you're having your conversations, if you're able to have it on the channel, that'll be very, very welcome as well. Thanks for your presentation, Praveen. It's exciting to see this work move forward. And I want to now hand it over to Neil. Neil, I know that we are behind, so the rest of the time is yours. So manage it as you see best, but go for it.
Thank you. Let me just get set here. I will request permission to present the slides. Let's see. Make sure we get the right one. Okay. Okay. Let's see. Is everyone able to see the slides? Can you guys hear my audio?
Yep.
Okay.
Visible.
Okay, great. So yeah, so I wanted to give a quick update about BBR work going on inside our team. And Ian will also be presenting some updates on the quick side as well. And I'll make this super quick. So I just wanted to talk a little bit about the deployment status, code status, and then give a super high level overview of the internet drafts that I updated the site last night. So you can find links on the ICCRG list and the BBR dev list. And the goal here is basically to mostly to talk about the drafts, which are responding to requests from the IETF community and other transport stack maintainers implementing BBR v2 that obviously said it would be useful to have a draft documenting the algorithm. And this is always part of the plan, and we apologize for this not happening sooner. And we also, of course, want to invite the community to read the drafts and offer any kind of feedback, both low-level editorial feedback, algorithm ideas or bug fixes, test results, anything is useful and welcome. So in terms of deployment status of BBR at Google, right now Google internal traffic is either using BBR v2 as a default, or it's part of a pilot program where we're gradually rolling out BBR v2, the Swift variant, which we discussed at a recent ICCRG. So the default right now is BBR v2 using ECN and loss and bandwidth and RTT as signals. but we are doing a pilot that is small but growing of BBR, a Swift variant that is using a sort of network RTT estimate as a primary congestion signal in the manner of the Swift algorithm that was published at SICOM in 2020. Google external traffic is still using BBR v1 by default, but we're working on transitioning that to v2, looking at A/B experiment, QoE and latency data, and iterating to improve that for the launch. And of course, we're continuing to iterate on some of the areas where we know we want to improve, including the issues that Praveen mentioned about coexistence with Cubic. I also wanted to mention we have, Praveen mentioned CPU usage, and we do have a patch set that introduces a fast path for BBR processing that we did find was useful in bringing the CPU usage to parity with Cubic for our, at least for our production workloads, which we will be sharing when we get time. Let's see, the status of the code. This is just a sort of repeat. We have open source versions. You can find the links in the slides. So the BBR functionality is sort of split between two different drafts, as it was in the original release for BBR v1. So the first draft is a delivery rate estimation algorithm, and that covers a bandwidth sampling mechanism that's used by both BBR version 1 and version 2. And it's also just generically available in Linux TCP. You can use those bandwidth samples no matter what congestion control is in place and being used. The algorithm is largely unchanged since BBR v1 times. There was a significant bug fix, though, that we've folded in and described. Basically, we realized that when the loss detection algorithm decides to retransmit something, that is another point when you need to look for bubbles of silence before that event, just as you would for cases where an application decided to send something. Anyway, so you can take a look at the draft and give us feedback. It would be appreciated. So the other piece of this puzzle is the BBR congestion control draft itself. That's also been updated to cover the current BBR version 2 algorithm. Right now, it just includes the aspects relevant to the current public internet. So the core model and the loss response and the strategy for coexistence with Cubic and Reno. The ECN part is only missing due to time limitations. That's still used at our site and still part of the long-term roadmap. We just haven't had time to put that in the draft. So I'll do, we'll work on that as soon as we can. And the algorithm is sort of documented in its current state, and of course there are some known issues. The one I mentioned here, it corresponds to the issue Praveen mentioned in terms of Cubic and BBRv2 coexistence, where Cubic wins too often. And then I'm just going to zoom through some pictures. Well, actually, first a quick outline. As you would expect, the draft sort of covers first an overview and then a detailed rundown of the algorithm, the network path model, how it sets the control parameters, and then the state machine as the algorithm decides to probe the network during its lifetime. And then I posted a couple pictures that I think, as pictures by themselves, they won't have enough context, but I'm hoping they'll be useful to folks who are making their way through the draft, reading the content, and they could use a little picture to help put everything in context and make it a little more clear. So this is a sort of high-level block diagram, if you will, about how the BBR algorithm fits in with its inputs and outputs and the basic structure of the algorithm, where it's taking various input signals, feeding it through a model and a state machine, and then generating the three control parameters: congestion window, pacing rate, and quantum or burst size. And then the next picture that I think might be useful to people is just a picture of the parameters in the model and how they fit together. And we don't have time to go into detail, but all of these are defined in the draft. And at a high level, you can say there's basically a set of parameters about the data rate that the algorithm thinks is appropriate, and then some parameters about the data volume, or amount of in-flight data. And a key part of that, of course, is the BDP estimate, but there are also other pieces that are discussed in the draft. And then there's just a little colorful picture of the state machine diagram that might be helpful as you're reading through the draft. And then here's also just a picture of a typical life in the day in the life of a BBR flow that sort of starts up. And this shows its evolution through the state machine with the level of in-flight data superimposed on top, so you can sort of get a sense of how these things interact. And again, we don't have time to go into it, but this might help visualize what's going on in the text of the draft. So yeah, in conclusion, we've updated the drafts to cover BBR version 2, and we look forward to feedback if people have time to read. And high-level feedback, low-level feedback, anything in between, it's all welcome. Yeah, thank you very much. And if there are any quick questions, I can take some, but let's also leave time for Ian to give his update about the quick side.
Neil, do you want to take questions now or wait until Ian's done?
Yeah, maybe let's wait until Ian's done. So I'll let's see, is there a way I can yield to
Yeah, just give it up. Folks, line up in queue if you want, but we'll wait until Ian is done before we take questions. Go for it, Ian.
How do I? Oh, there you go. Okay. Just grabbing my slides. Great, must be these. All right. So I've been working on a variety of small changes to BDR-2 that don't substantively change kind of the core algorithm and the approach that Neil outlined. But they do make some tweaks kind of around the edges, and some of those tweaks may or may not end up being particularly relevant, particularly in the public internet. So I'm going to walk through 3 today. There are a number of others that I haven't had time to outline, and also a number of others that I do not yet have good QB experience for. So yeah, let me go for it. So the TLDR is basically that BBR-v2 is very, very close to achieving the same YouTube video QE as well as search latency as BBR-v1 with these tweaks and a few others, but these are kind of the most substantive ones probably to highlight. And there are still some differences between the two. In particular, we expect that there will be a bandwidth regression between the two algorithms, just because that's kind of the intent. And I think that's deemed hopefully acceptable. But the key issue is that rebuffer rate and those other metrics are not seriously harmed as a result. And similarly for search, search actually has been a little bit easier, at least so far it looks like, and possibly due to the fact that BBR-2 is a little bit less aggressive. Search latency seems to be pretty robustly pretty close to neutral. So whenever we launch it, we'll release full details, but it's not a major concern at this point. So the video queue is more the problem. One challenge is today when you exit startup due to loss, you set in-flight high to BDP. That means that unless you are extremely nicely clocked in an extremely smooth manner, you are going to be C-win limited before you ever achieve the max bandwidth. That kind of is resulted in BDP. And similarly, once in-flight high is low, it can be very difficult or even impossible to grow it substantially. So this can sort of result in this sort of bandwidth crash thing where you have a certain bandwidth and then you each crank down the in-flight high. And then the future bandwidths actually keep going lower because in-flight high is so low that you can't actually achieve the bandwidth that you first achieved. So my proposed fix is relatively simple, which is you track the maximum bytes delivered in a round, not the max in-flight, to be clear, the max bytes actually delivered. So that should indicate that the pipe is at least that large because it actually delivered that many bytes in one round. And as a result, you have a lot less of a bandwidth crash when aggregation is present, and as well as like when you have excessive loss. So this seemed, this change, at least in our experience, improved QE and had almost no downside. The change in the retransmit rate was extraordinarily small. So I think Niels actually has plans to like start experimenting with this at some point, but it's kind of one of many smaller changes. There are a few other spots in the code that one could potentially start using this max delivered in round or rely more on bytes delivered rather than like in-flight and other metrics. And I have some experiments to work with those, but the results are less clear than they are with this one, where this one kind of was a pretty clear one. So the next one that's an issue that Niels talked about a few times is early prob exit. And similarly, like the lack of in-flight high growth during prob up, which is kind of related. So prob up can exit early due to queuing. The queuing criteria is you exit prob up if it's been at least min RTT in prob up. And to be clear, prob up in these slides means probe BW : up from Niels' slides. And the bytes in flight are greater than 1.25 times BDV plus 2 MSS. So if you're not in probe up, you don't really increase in-flight high. There are some ways it can increase, but typically it's quite rare. And again, you never kind of re-achieve the max bandwidth. So the simple solution that we currently have in our code, default enabled, is you wait at least one round instead of min RTT. In cases when there's a lot of aggregation, the min RTT can be an order of magnitude smaller than the smooth RTTs. That kind of ends up being necessary. And then you put on the extra act for the in-flight check. This isn't perfect. This does increase retransmit rates somewhat measurably. It's still massively less than BBR1, but this extra criteria is, in some cases, a little bit aggressive, but it at least is proof that there are solutions out there that kind of like avoid this early exit and don't cause like a huge amount of collateral damage. A newer idea that I wrote relatively recently is instead of looking at the extra act, what about looking for a persistent queue over the course of the round? And so the code says if you've been in probe up for at least a round and your min bytes in flight are greater than kind of the 1.25 BDP number that we're already checking against, then you exit. In theory, this might allow us to skip the application limited check in various spots. There are some spots in startup as otherwise that we do app limited checks. If you were app limited and you still couldn't get your queue under the target, probably something's not going great. And so making the code a little less sensitive to app limited checks is kind of a potential side benefit of this. And yeah, the last one was excessive time in probe RTT. This one's pretty simple. Basically, when you're coming out of quiescence and you're in probe RTT, you don't leave until like a full round is passed, because you need an ACK to kick yourself out of probe RTT. And so that means you're sending it like well less than half the bandwidth for a full round. We independently discovered this apparently in TCP and Quick. So apparently it was a good idea. And yeah, TCP already has this fix in as well, but it's kind of worth noting just because it can increase the amount of time in probe RTT when you're doing app limited traffic. And we noticed this in a number of YouTube flows where you'd get a chunk and then stop for a while and get a chunk and so on and so forth. And when you finish the last chunk, you'd still be in probe RTT. Cool. So that's it. I want to open up the floor for questions. We have 7 minutes left.
Sweet. Thank you. All right. Jonathan, you're up. Neil, do you want to join?
Yeah. I was wanting to ask about the ECN, since it isn't in the draft yet. Could we have a brief summary of how ECN information is incorporated into the algorithm and how it differs into how loss information is incorporated?
Right. The ECN information is interpreted in a manner that's very similar to DC-TCP. So I think that tells you all you need to know. Right now, there's no, it's not L4S specifically, just because there's no, it's not tied with the ECT1 code point, and it's not integrated with accurate ECN. But the intent is to allow it in the future to be L4S compliant down the road.
Right, and that differs from how loss information is incorporated, right?
Yes. Yeah. Did you want? Well, I don't know if we have time to go into the specifics, but the reaction to the ECN is very similar to DC-TCP. So there's a every round trip where there's ECN marking, there's sort of a multiplicative decrease that's proportional to the exponentially weighted moving average of recent ECN marks. So yeah, so hopefully that's a quick summary. There are also details about it, I think, in previous ICCRG slides. But I'll also try to update the draft to discuss the ECN part as soon as we get cycles.
Yeah, it's probably a good idea to put it in the draft. Vidhi, you're up next.
I was actually going to ask about which form of ACN are we using, but Neil already answered that. And you said there's plans to use accurate ECN, right? If accurate ECN is supported, so that's good. The second question I had is, oh, sorry, go ahead.
No, I was just going to confirm that. Yeah, so I think if and when accurate ECN makes it into Linux or other OSs, then yeah, the plan would be to use that signal. Yeah.
Okay. The second question I had was regarding the points that Ian noted about in-flight high. So is the in-flight high not set again after the loss? Like I was assuming it would be set again. You know, once you have a loss, sure, you set it to BDP, but then you have probably another stage where you would increase the in-flight high. Or am I understanding it?
Yeah, that's correct.
Going to probe up, but I'll let Neil answer.
Yeah, you're correct that the flow probes again, but the tricky issue is that there's sort of a coupling between the in-flight high value that's bounding the amount of the volume of data that you're willing to put in the network, and then your bandwidth estimate, which is the rate, the delivery rate that you can achieve. And once you've decided you can only fit a certain amount of data inside the network, then that implicitly bounds the rate that you're able to achieve. And then because it's bounding the rate you're able to achieve, that bounds your estimate of the BDP. And then that in turn bounds the amount of data you're willing to put in the network to probe for bandwidth, and causes you to not put enough data in the network in order to achieve a higher delivery rate and raise your bandwidth estimate. And so you can sort of, with the current logic that's in place, you can sort of get stuck sometimes if there's a packet loss early on that can limit your sense of the safe volume of data, which limits your bandwidth estimate, limits your probing, and you kind of get stuck in these cases. You know, there are a couple of different ways you can fix that. And you know, Ian and I are both continuing to experiment with that. It gets a little tricky though, because then once you fix that, which I think is fairly straightforward to do, then it impacts your coexistence behavior with Cubic and Reno, because then you end up causing packet loss more often. And so I think the algorithm might need to be a little more shrewd about how it schedules its bandwidth probing once it's more robust about pushing up to encounter loss in these cases.
Thank you. Yeah, that's a great insight. Thank you.
Yeah.
Praveen, you're up.
Yeah. Hey, thanks, Neil. Really appreciate the new drafts. I will certainly go over them, provide my feedback. One quick question on the logistics. So do these drafts reflect the code that's in the sort of out of kernel repo that we are using as the basis, or is this reflecting work that is not part of that code? So that was one question. And I also had a suggestion for Ian is to, like, you know, whatever enhancements you've made, you know, bring them to ICCRG to the draft. Having quick and TCP converge to the same thing would be extremely useful.
So that is the intent. As soon as these things are kind of proven to work well in both TCP and Quick, we're going to make sure they make it into the draft. But we're so far been a little bit conservative and tried to make sure that we're very sure that like any change we make really like works well in a variety of robust circumstances. And Neil has a variety of simulations and test scenarios that I don't easily have available to me, and kind of vice versa to some extent. And so we kind of need to make sure that something I change that like works great for YouTube doesn't like destroy like data center applications. So we do need to kind of go back and forth, and I think that'll take some time.
Right, well said. And then, so the question about which version, yeah, this should correspond very closely to the code that's currently on GitHub. There may be one or two small differences where there are two different behaviors available in the GitHub code, and the draft documents the one that we currently recommend. But otherwise, it should be very similar. Thanks.
I'll short my question. So you're implying that the Quick and TCP implementation is diverging a little bit, and obviously there's a practical issue there. But is the different are the differences solely related to the applications involved, or are you seeing like protocol specifics that are driving these divergences?
I mean, I'll let Ian give his perspective, but my perspective is that we just have a team with multiple people who are both doing experiments on a continuous basis and just in different code bases. And, you know, Quick is probably able to get experiments pushed to front-end servers faster because it's user space code. We have some different tools for the TCP side that can help explore other scenarios. So I would view it as a collaboration, and both of us are running experiments to sort of move, you know, figure out how to improve the algorithm. And then, as Ian said, once we gain confidence with one particular approach, we're going to make sure that the TCP and Quick versions of the algorithm agree. And likewise, if there are other people out there doing BBRV2 experiments, we want to make sure we're incorporating any good ideas that are out there in the external research community as well.
The only thing that's a really protocol difference I can think of that we do observe some of is, as you probably know, Martin, ACK decimation, ACK frequency, whatever you'd like to call it, is quite widespread for Quick. Similar approaches are fairly widespread for TCP, but they kind of, the way they manifest themselves are a little bit different. And that, along with like some of the scheduling being user space, means that I think the traces and the ACK lines tend to look a little bit different. And I think Quick suffers a little more from the aggregation effects on the public internet due to a variety of these factors. So my experience with BBRV1 is Quick was impacted more by aggregation.
Yeah,
so that's the
that's
one
definitely
difference.
Yeah, although it's interesting because inside in the data center case, TCP also does see massive degrees of aggregation, because when your RTTs are super small in the data center, then the aggregation that the NICs are doing or your software is doing then becomes massive in the traces again at these very tiny RTTs. So yeah, so I think there's plenty of aggregation on both sides, and I think yeah, I'm sure we'll be able to coalesce on a single final algorithm. Yeah.
Thank you for that, and I want to thank Neil and others on pushing a new draft. And I will also say that if you don't, I'm going to start requiring you to have all of your discussions on the mailing list so that somebody else can copy them and turn it into a draft. But thank you for all the presentations, and thanks Neil, Ian, and Praveen for shortening your discussions and allowing the first timers to take some more time to present their stuff. But I want to thank everybody for being here. This was a fantastic session, and I look forward to more discussions. I've just created a Slack channel, so use that as well. And we'll see you next time.